Okay, so chapter 15 is going to develop the model for statistical significance testing, present some various points, and most importantly, demonstrate our first statistical significance test. So the hypothesis testing model could also be called a model for statistical significance testing. And we've got 4 different steps. First, we're going to state the hypothesis pair, the null and alternative hypotheses. We need to select a significance level. The third step is to carry out the appropriate test. There'll be different tests for different situations. And finally, we will make a decision on the hypothesis pair. Most of this chapter is going to go over in considerable depth the large sample test of the mean, or we can say the large sample test of X bar. And this test examines whether the mean of a randomly selected sample differs from some hypothesized value. Now, prior to jumping in to the large sample test, we need to talk about the notion of assumptions of statistical significance tests. So assumptions are conditions that must be met for a test to yield an accurate probability, an accurate p-value. Now, an important assumption in statistics is the normality assumption. And this assumption is that the population from which the study sample is selected has a normal distribution. This assumption is a key assumption of the large sample test of the mean. Sometimes a statistical significance test is robust to an assumption. Now, when a test is robust to an assumption, failure to meet that assumption has only a minor impact on the accuracy of the test results. Predominantly, we're meaning only a minor impact on the p. So, if indeed an assumption is violated, but a test is robust to that assumption, then in that situation you can go ahead and carry out the test, because the robustness to the assumption tells you that your results are going to be very, very accurate, even though the assumption hasn't been met. On the other hand, if an assumption is not met and the test is not robust to the assumption, then you should not carry out that test, because your results will be inaccurate. Now, some assumptions are common to all statistical significance tests. So, for instance, we talked about random sampling being a requirement, and that random sampling included such things as selection by a method of chance, all cases having an equal chance of selection, and independence of selection. And as you recall, we're not studying random sampling in depth here, that is to say, different types of random samples. So we are, in effect, in this text, as chapter 12 discussed, I mean, we're presuming that we're working with what are called simple random samples. But I simply call those random samples rather than getting into the specifics of simple random sampling. And then we talked also in chapter 12 about independence of observations. And as an example to recall that, a very obvious example of violation would be if a student copied from another student on a test. Then the test scores of those two students would not meet the independence of observations assumption, and therefore you should not carry out the statistical significance test in that situation. More explicitly, I mean, we would throw the copied test out. That would be the pragmatic way to deal with that. But the above assumptions are common to all tests, and at least they're common to the introductory tests that we're discussing here. You can get into nuances as you get into more and more complicated stuff. But so for our purposes, they're common to all tests, so we don't need to mention them further. Let's talk about the assumptions for a large sample test of the mean. Though not an assumption per se, a requirement of this test is that n be greater than 100. Now, if indeed n is greater than 100, then it is the case that the large sample test can be carried out even when the shape of the population from which the sample is selected is non-normal. Hence, presuming that n is greater than 100, our large sample test is going to provide accurate results for just about all shapes of distribution encountered in social science. So your population from which you're selecting your random sample might be strongly skewed, have a uniform shape, it might be very peaked, or just about any shape encountered in social science research, you're going to get accurate results for a large sample test in these situations, provided that n is 100 or greater. So if n is 100 or greater, then the large sample test is robust to the normality assumption. Let's develop a working example for our large sample test. So let's presume that there are 100 randomly selected parents in the large town where you live, and that these 100 parents participate in a parenting skills intervention that you develop, and that following your parenting skills training seminar, or whatever precisely your intervention is, they're going to take a parenting skills scale, and here are results on that scale. The mean, these 100 parents turns out to be 105, and the standard deviation of scores on the parenting skills scale is 20. Now, to continue developing our example, let's suppose that this very same parenting skills scale has been given at some prior point in time to a very, very large national random sample of parents, of kids of the same age as the parents in your sample. So the mean score in your sample is 105. The mean score in the very, very large random sample of parents across the country is 100. These two mean scores differ. So the question that our large sample test is going to examine is basically, well, how likely is it that this difference of 5 points might just be due to chance alone? Is this difference a large enough difference that we can be confident that it doesn't just reflect the effects of random variation? Well, let's go forward with our hypothesis testing model. So step one calls for us to state the hypothesis pair, and let's use a non-directional pair, and our null hypothesis is going to be that the mean of the population on which our random sample was selected is 100 points. Now, so if I state that differently, it would be that in the population of parents in your town from which you selected your random sample, in that population, the mean is 100 points. And an alternative hypothesis is going to negate, which is to say state the opposite of the null. So our alternative hypothesis is going to state that the just described population mean does not equal 100. Now we're starting to use more symbols now as compared to chapter 14. So let's go over some of these symbols. HO is the symbol for the null hypothesis. Recall that the Greek letter mu symbolizes the mean in a population. H1 is the symbol for the alternative hypothesis. Let's go ahead and state the hypothesis pair in words. I guess it's what I just said. So the null, the mean parenting skills score in the population of all parents of elementary school children in your city equals 100 points, and the alternative states that this is not the case. Step 2 is the choosing of a statistical significance level. Let's choose the 0.05 significance level. This is the most commonly used level, and there's the Greek letter alpha. And so we're saying alpha equal 0.05. We're setting alpha to 0.05, which is the same thing as saying we're setting the significance level to 0.05. Well, we're going to keep working on some theory. So, I mean, we're going to, in essence, sort of carry out our significance tests theoretically. So we might ask the question, given a true null, which is to say, given that the mean in the city population of parents really does equal 100, well then, if you drew an unlimited number of random samples from that population, what would be the sampling distribution? So this distribution is sort of going to show us the workings of chance, if indeed the null were true. So let's go ahead and use our knowledge of the central limit theorem to work on the characteristics of our sampling distribution. Point 1 of the CLT states that the mean of the sampling distribution equals the population mean, which is to say the mean of the population from which the samples are selected. So the mean of our sampling distribution will be 100. Now point 2, and then some subsequent information provided, states that we can get a very good estimate of the standard deviation of the sampling distribution by taking the standard deviation in our particular random sample and dividing by the square root of n. The standard deviation of the sampling distribution is called the standard error of the mean, and here's the symbol for our estimate of the standard error of the mean. And this estimate is a very good estimate, providing that sample size is 100. So in your random sample, the standard deviation of parenting skills scores was 20, so we're going to divide by the square root of the sample size, and 2 is a very good estimate of the standard deviation of our sampling distribution. And finally, our sampling distribution will have a shape close to normal. And we know that basically from step 3 of the central limit theorem. So, if the null is true, our sampling distribution would look like this. And here's the summary information. A mean of 100, a standard deviation very close to 2. We don't know that it would be precisely 2 because we're getting a very, very good estimate of the standard deviation. And finally, a shape that is very close to normal. And do note that we've got a second x-axis just showing how many standard deviations above or below the mean a given score would be. So for instance, 102 is 2 points higher than the mean of 100. The standard deviation is 2, so it is 1 standard deviation above the mean, and therefore its z-score is 1. Let's add a little bit more detail to our depiction of the sampling distribution. So recall from Chapter 13 that in a normal distribution, 95% of the cases are located within 1.96 standard deviations of the mean. So that we could go up 1.96 standard deviations, and that would take us to here. Or, on the other hand, in the negative direction, 1.96 standard deviations. I mean, 1.96 times 2 is 3.92, so we subtract 3.92, and we come actually over here to 96.08. So here is our other 2.5% tail. So we've got 95% of the cases within 2 standard deviations, and then 2.5% cases, 2.5% of cases more than 2 standard deviations from the mean. And those are our 2.5% positive and negative tails. Okay, recall from the last chapter that statistical significance testing, and what I'm really meaning to say is the value of P, the probability of the study sample result, has to do with the percentage of cases in the sampling distribution that are more extreme than the study sample result. Now we're going to consider both directions with a non-directional pair. But for instance, our study sample mean was 105. Now let's just do some math quickly in our head. The standard deviation of the sampling distribution is 2, so that 5 points greater than 100 is 2.5 standard deviations above the mean. So our study sample mean is 2.5 standard deviations above the mean. Now, on the other hand, when we think about the probability of a particular result with the non-directional pair, we consider both directions. So we could also come to a score of 95 that's equally extreme in the opposite direction. Now, where are these 0.62% coming from? Well, one would go to the normal distribution table at the back of the book and find a z-score of 2.5, and you would see that 0.62% of cases, I mean that's less than 1% of cases, have z-scores greater than 2.5, and then because our distribution is symmetric, you know that the equal percentage have z-scores of minus 2.5 or below. So we can divide by our percents by 100 to get our probabilities. So here are the probabilities of, well, let's call this the probability of the negative tail, and this the probability of a result in the positive tail. We sum those probabilities to take both tails into account, and so we could answer the question, what is the probability of obtaining just by chance, by the luck of the draw, given a true null, a study sample mean that is as extreme as our obtained mean or even more extreme? And that probability works out to 0.0124. So that probability is just a little bit greater than 0.01. So in our example, P equals 0.0124. Repeating some ideas that we talked about in the last chapter. Basically, in a two-tailed test, which is to say when we have a non-directional hypothesis pair, we look at both tails. So what is it that makes a statistically significant result? Well, basically, results near to the center of the sampling distribution, I mean near the high point of our bell curve, well, these results are quite consistent with a true null. I mean, the luck of the draw very, very often produces these kinds of results. And then as you move further from the center and going in both directions, that is, as you move towards the tails, the results are becoming increasingly less consistent with a true null. In other words, that less and less often does the luck of the draw produce such results. And finally, as you keep moving towards the two tails, the result becomes sufficiently inconsistent, or we can say sufficiently extreme, for the null to be rejected. In other words, it's out so far that we would say to ourselves that the luck of the draw hardly ever produces results this extreme. Therefore, it's likely that the null is false. So I guess we do need a definition, which is the definition of a two-tailed test. And when results in both directions can result in rejection of the null, the significance test is a two-tailed test. Two-tailed tests go hand in hand with non-directional hypothesis pairs. The alternative hypothesis simply states not equal, so the result in essence can be not equal in either the negative or the positive direction. So with the non-directional pairs, we consider both tails of the distribution, and therefore the term a two-tailed test, or occasionally you'll hear a two-sided test. So how do you look at statistical significance, and in particular the value of p, when you've got a directional hypothesis pair? Well, when results are near to the center of the sampling distribution, and also when results are in the directions stated in the null. So the null is going to state the direction opposite to expectations. Our alternative hypothesis is stating the direction of expectations. So if you're getting results that are near the center of the distribution, or results that are in the direction stated in the null, these results, from the perspective of a directional pair, are consistent with the null. Now, as results move away from the center of the distribution only in the direction stated in the alternative, the results are becoming less consistent with the null. And then at some point, results become sufficiently inconsistent, sufficiently extreme for the null to be rejected. And the results can only become extreme as they move in the direction stated in the alternative. So in a directional hypothesis pair, only results that are in the direction stated in the alternative are viewed as inconsistent with the null. Further, we can state with a directional hypothesis pair only results in only one tail. I mean, the tail in the direction of the alternative result in rejection. So with a directional hypothesis pair, the statistical significance test is a one-tailed test. And it's again a one-tailed test because results in only one tail can result in rejection. Let's define rejection region or regions, because with a two-tailed test you're going to have two regions. These are the areas of the sampling distribution that result in rejection of the null. Now, for both two-tailed and one-tailed tests, the proportion of cases in the rejection region or regions equals alpha, where alpha is the probability connected with the significance level. For instance, if you select the 0.05 level, which is the same as setting alpha to 0.05, then the proportion of cases equals 0.05. If you select the 0.01 level, which is to say set alpha to 0.01, then the proportion of cases in the rejection region or regions equals 0.01. So our table here is showing the relationship between the type of hypothesis pair and the ultimate location of the rejection region. So let's just go through one of the examples. So suppose your hypothesis pair is non-directional. What direction do you expect the study result to be in? With a non-directional pair, there is no direction of expectation. The idea is the study result could be in either the negative or the positive direction. And here are our mathematical operators, or we can say logical operators, equal and unequal. We have a non-directional hypothesis pair, therefore our significance test is two-tailed. We're considering both tails. Now suppose that we choose the 0.05 level. What are our rejection regions? So in our first example, the rejection regions would be the upper and lower 2.5% tails. We're dividing 0.05 in 2 to get the 2.5 upper and lower percent tails. And let's do another example. So for instance, suppose you have a directional hypothesis pair. And with a directional pair, that means you do have a direction of expectation. So let's presume that that direction is greater than. So the logical operator for the null expresses the direction opposite to directions, the less than or equal condition. And here is the logical operator for the alternative, conveying the direction that we expect the results to be in. Directional hypothesis pairs go with one-tailed statistical significance tests. So we're going to have a one-tailed test, and then in this particular example we are going to set alpha to 0.01. So if alpha is 0.01 in this situation, then our rejection region is the upper 1% tail. It's the 1% tail because the significance level is 0.01. It's the upper tail because our direction of expectations is greater than. So I'll just let you study this table for a few seconds before we go on. So as we conclude this video, what we're going to do is, in essence, carry out the significance test using the sampling distribution. So we're kind of carrying it out visually or intuitively, perhaps. So what are our rejection regions going to be? So recall that our example is using the 0.05 level and that our hypothesis pair is non-directional. And our example again is this parenting skills example. So what we need to do to get to the upper 2.5% tail is to go up 1.96 standard deviations. And so you'd multiply the standard deviation of 2 times 1.96, and that would basically be telling us let's go up 3.92 points. So we've got to go up to 103.92 to reach the upper 2.5% tail. And then we've got to take that similar amount away to define the lower 2.5% tail. And then what we're going to need to do is we're going to need to look at our study sample result and see if it is in a rejection region. And we're going to find out it is indeed in the upper rejection region. So here's our result visually. The shaded areas show the upper and lower 2.5% tails, and those are our rejection regions for this example. Then we plot here our study sample mean. Our study sample mean is indeed located in a rejection region, and therefore our decision is going to be to reject the null hypothesis and accept the alternative. And so, I mean, just intuitively, we're going to reject the null at the 0.05 level when the probability of obtaining the result due to chance alone is less than 5 times in 100. So these rejection regions are showing, in essence, the 5 times in 100. Given a true null, only 5 times in 100 do you get a result in a rejection region. So our result is unlikely to be due to chance. A result as extreme as our result, or even more extreme, occurs less than 5 times in 100. So we are going to reject the null and accept the alternative. So we're going to conclude that the mean in the population in your town does not equal 105. So that's the next thing what we're going to need to do is carry out the test, in essence, not visually, but more straightforwardly using a formula. And we're going to need to carry out the test showing you how it works with one-tailed situations and when we vary the significance levels, say at the 0.01 level rather than the 0.05 level. But that's it for now.